Let's talk about electrophilic aromatic substitution, or EAS, as we will abbreviate it. In this set of reactions, benzene is going to act as a nucleophile and react with a variety of different electrophiles. And in doing so, we can brominate it, chlorinate it, add a nitro group or a sulfonic acid, or we can add a ketone or an alkyl group. So we have quite a variety of different things we can do with our benzene. In all of them, benzene is your nucleophile, and the mechanism is exactly the same, except for the generation of your electrophile. We're going to see that we can generate electrophiles in various ways, but once the electrophile is generated, the mechanism is going to be identical for all of these. And so we have to consider that we looked at trying to brominate via addition before. We tried to think, okay, well, maybe we can get to put some bromines on this thing, get an addition product. But because that ruins the aromaticity of the compound, it's energetically unfavorable, and so it doesn't happen. That said, we'll see that, interestingly enough, if we take that same benzene and try to brominate it in the presence of some special catalysts, we will in fact get a reaction to happen. So if we take benzene and react it with Br2 with iron or aluminum, we will in fact be able to substitute on our benzene. We will actually be able to install a bromine on one of the positions of the benzene. And we're going to see that this iron or aluminum can come as the metals themselves, or more commonly, you'll see the various 3+ salts of those ions. And these are going to be acting as catalysts. So we don't need a stoichiometric amount of them. They're just there to facilitate the reaction happening. And we can first take a look at what's going to happen when a bromine molecule interacts with iron 3 bromide. So if we take consideration of FeBr3, we have a nice trigonal planar molecule. I'm not drawing the bonds correctly, but that's okay. Because what's important here is that we have this kind of empty spot here, right? Normally, we like to have octets on things, right? Even if we have a metal there. And we're going to see that because this is an empty kind of orbital, this functions as a Lewis acid. And Lewis acids can be attacked by a Lewis base. Remember, Lewis bases are electron donors, Lewis acids are electron acceptors. When we have these complex together, of course this is an equilibrium process, but we will end up having the following. We'll end up with a positively charged bromine, which actually what we'll see is going to happen is the electrons are just going to go from the bromine-bromine bond. It's going to break homolytically and all of the electrons will go to, heterolytically, will go to the positive bromine in order to stabilize it, thus kicking out one bromonium ion, or rather a bromine cation. So overall we have this negative complex, and we're left with a bromine with only 6 electrons and a positive charge. And so, as a result, this now is an excellent electrophile. Notice that when we used bromine, just Br2, it's not really a great electrophile, right? It's a mediocre one. We're just taking advantage of the fact that, just due to van der Waals forces, we occasionally have a slight positive charge. But now we have a bromine ion that is fully positively charged. And that's an excellent electrophile. So let's see how this is going to react with benzene. When we take benzene and have an electrophile nearby, a strong electrophile, the benzene will go ahead and grab it. And in doing so, our benzene is the nucleophile. Remember that pi bonds are a source of electron density. So we're going to go ahead and attack our bromine ion. And in doing so, don't forget we still have that H there, right? We have an H on both of these. Once that bond goes to attack the bromine, we're left with a carbocation on our molecule. And of course, we have destroyed the aromaticity, right? So there is definitely an energy barrier to doing this. That's greatly facilitated by having the electrophile be very strong. A strong electrophile is strongly reactive. It's going to help convince the benzene to react. And interestingly, of course, because this is now an allylic carbocation, we can have resonance happen. We can resonate our carbocation around, thereby stabilizing it, which is going to help out in this process. So we've moved our double bonds. We now have our positive charge over here. So notice that this cation is resonance stabilized. Carbocation. It's resonance stabilized. And of course, there's a third place we could put the positive charge, right? We could put the positive charge opposite side of the bromine through resonance as well. So we definitely have that option. We call this resonance stabilization, it's called a sigma complex, where we have this positive ion that's able to float around the benzene. So we have three positions that can be resonance stabilized if we ignore everything else. Remember, if we have our carbocation there, we can resonate it so that it is now on the opposite position. So if we do that, we're going to now have our carbocation on the opposite side. And we can resonate this some more. If we resonate it again, move that double bond over, we will now have our carbocation on the other side of our newly added substituent. And so this is called the sigma complex. You might see it just called an arenium ion as well, because remember, aryl stands for benzene, right? And so this is an arenium ion. It's just called a sigma complex, and it's stabilized by resonance. So this is showing us why we're able to do this, because yes, we are generating that cation, we are removing the aromaticity, and but we're able to stabilize that cation. And now, at either of these, our next step of the reaction is going to take place. So if we just assume that we have that rightmost one, resonance form, it doesn't matter. Either the first or the leftmost or the rightmost will work. We have our carbocation here. And in fact, I'm going to just switch the X and the H. In this case, it's our bromine, right? So I'll actually put that in. What happens now is our lovely catalyst comes along, the iron that has too much electron density, and we're now going to have it dissociate one of the bromines, and we're going to end up having it abstract the proton at the position that was brominated. And in doing so, we are going to reform a double bond. We're doing an elimination here. And we're going to reform that double bond and restore the aromaticity. Notice our FeBr3 is regenerated. That's why it's a catalyst. It's not consumed in the reaction. It's just helping this process along. we also will lose HBr as a byproduct. But now we are left with our happily substituted benzene. So let's recap this mechanism. First, we form our electrophile. That's that Br+. It's only got 6 electrons, so it's just aching to complete its octet, and benzene can do so by attacking it. By attacking that bromine, it's now going to satisfy the bromine, but we're left with the carbocation on the benzene. That carbocation can undergo a series of resonance steps to stabilize itself, to delocalize. And in 2 of those resonance forms, again, there's equal chance, we're able to then eliminate our hydrogen using a bromide ion. Bromide is not a very good base, but the fact that we're restoring aromaticity to our benzene is a very strong driving force. So it's able to do so. In this reaction, we therefore produce an HBr molecule as a byproduct, and we regenerate our iron 3 bromide catalyst. And we're going to see this is exactly the same mechanism for chlorination. If you take benzene and try to add chlorine to it, you will. It will work. This won't work with other halogens, though, only bromine and chlorine, but we'll see there are other ways to add other halogens on. And so, in the process, of course, we will also make an HCl molecule, just like we made an HBr before. And the mechanism is exactly the same. The chlorine will complex with the iron, form a chlorine ion, chlorine positive, which will then be attacked, form a sigma complex, and then eliminated, forming the HCl. And so in either case, it'll work. And remember, your catalyst can be any. You can use Fe, you can use aluminum, or you can use the metals themselves. So any of these 4 catalysts will work. If you're doing chlorination, you want to have chlorines on your iron, if you are, or aluminum. If you're doing bromines, you'll want to have bromines on there, of course, because otherwise you'll end up with a mixture of products. So either any of these catalysts will work. One final note, this reaction will also happen in the presence of electron donating groups, and you don't actually need the catalyst. In the presence of an electron donating group, this is something we're going to look at later, but what will happen is we will end up being able to brominate it without the catalyst. We're going to see that electron donating groups will help this reaction to happen, although we will end up with a mixture of regiochemical products. And so we'll see this later on when we talk about effects of other substituents. But since this is related to the bromination, when you have an electron donating group on your benzene, you do not need the catalyst anymore. But you do need the catalyst if you are dealing with naked benzene. And so this covers bromination and chlorination, as well as our generic mechanism for electrophilic aromatic substitution. First, you make the electrophile. Benzene attacks the electrophile. We form a sigma complex as a resonance stabilized cation. And the last step, you eliminate. In doing so, you restore the aromaticity as the driving force for making this reaction happen. In our next videos, we'll take a look at nitration and sulfonation. And we'll start with looking at how those electrophiles are made.